And this one, we know this limit equals 0, right? By the sandwich theorem or the squeeze theorem. This equals 0. This equals 0. So that is this derivative equals 0. However, as x approaches 0, this limit does not exist. The limit of this one as x approaches 0 does not exist. This is because this limit equals 0, but this limit, which is similar to cosine of 1 over x, is similar to sine 1 over x. It also oscillates near 0, between -1 and 1. This does not exist. So that is, f is everywhere differentiable but it is not continuous at 0. So for a real function, even if it's everywhere differentiable, its derivative may not be continuous. I'm sorry, its derivative, I'm sorry. Somebody's looking at me. Its derivative, f prime, right? Of course, f is everywhere continuous, right? Its derivative is not continuous at 0, right? So even if it's differentiable everywhere, it may not be, its derivative may not be continuous at a certain point, right? However, I know you think that there's so many things. So f prime is may not be continuous, right? But it verifies the so-called intermediate value theorem. So which states if f prime of C is less than or equal to k, less than or equal to f prime of d, then k equals f prime at a certain x for some x in CD. This is a property verified by continuous functions, right? In general, if a function is not continuous, it's not true. Right? What's the meaning of this? So that is, for this function here, this is C, this is D. So this is f prime of C, this is f prime of D, those two values. And k is just some value in between. And then this k must be taken by f prime somewhere. Right? For continuous functions, that's true, right? It's the intermediate value theorem, right? But here we have this example shows the derivative may not be continuous. But even if f prime is discontinuous, it still verifies this mean value property. I don't want to do the proof, but you can tell from here, right? This derivative is this function, right? It's more or less like this one, which is like 0, minus this cosine. It's graph more or less close to this, right? It sweeps out, no matter how small a neighborhood is, it sweeps out all the values from -1 to 1, right? It won't leave off any intermediate value unassumed, right? Right? It takes all the values between -1 and 1, even if it's discontinuous, right? I mean the derivative, right? So that it verifies the intermediate value theorem. However, it may not be continuous. And another thing This is for real function. I'm going to shamelessly advertise the course I'm going to teach. So this is f defined on some subset of the complex set of complex numbers for a complex function. So f is differentiable on omega. Omega is an open set. That implies f prime is continuous on omega. And well, this is the first assumption, right? Because here, if for a real function is not true, right? Even if it's everywhere, this example shows even if it's everywhere differentiable, its derivative may not be continuous, right? But for complex functions, it's totally different. If it's differentiable everywhere, then the derivative is continuous. This is called the Goudard's theorem. Right? And then if the derivative is continuous, that's a continuous differentiable, then that is f is analytic. In particular, is C infinity. Its derivative of any order exists. Analytic means you can write it f of z as a power series. Right? That's the meaning of analytic. Analytic is stronger than C infinity, right? So this theorem is called Cauchy's theorem. In complex variables. And you can say there's a great difference between real functions and complex functions, right? So basically, you just think about this. For a complex function, if it has a first derivative, then it has second derivative, it has a third derivative, all derivatives, and you can write it as a power series. For real functions, that's not true, right? Absolutely, this is absurd for real functions, right? But for complex functions, that's the truth. Yeah. So that's a big difference. Okay? So right now we are in reals, right? We are in reals. We just you can forget this, right? But you need to know this.